Georgios, welcome.
Thank you. I'm Georgios Pitsiladis from Greece. Now, this talk will be different than the others, both in the path that it wants to take and probably how far it has treaded this path. The intent is to formalize the mathematical discourse in some way, so mostly it has to do with mathematical knowledge management than with linguistics per se. And the idea was of my professor, Petros, based on the work of his professor about proof events. Now, John Morgan wrote a small essay back in around 2000. The last edition was in 2001, where he argues that mathematicians talk of proofs as real things and syntactic, but actually what happens in the world is proof events, where some mathematicians utter something which might be words, formalized, non-formalized, images, gestures, and some others listen to that and interpret it, and maybe they agree, they take it as true, as false, or something in between. So he dubs the element proof object, which might be text, image, etc., and the event proof event. Now, Stefaneas and Vandulakis have tried to present a first formalization back in 2015, in which a proof event contains two agents, a prover and an interpreter. The prover wants to argue about a problem, time-independent problem, formal problem, if you like, and presents an intention, which is the proof attempt. It might not be a complete proof, it might be just an idea. It might be a wrong proof. It's articulated in some language. This happens at the time, and the interpreter then interprets the utterance of the prover and assigns a value which measures the subjective conviction in the truth of the proof and the problem. Now, in reality, this happens in two different semiotic spaces. That is, the prover understands the world differently than the interpreter, but for simplicity, we'll consider one interpretation. I believe the interpretation of the interpreter is suspect. Now, of course, this can be extended if we like by considering more timestamps, since there are more than one time events happen. The statement and the validation may be multiple months apart or years. But for simplicity, let's stay with one timestamp. And of course, if we want to extend the framework further, we must consider multiple agents. So multiple timestamps, there is some community, so there is much to be done there, but we'll stay with two agents here. Now, I chose to discern between two kinds of proving events. Proof events where we try to prove, and these proof events where we try to disprove. Because that happens in mathematics, there are some cases where you won't end up saying that, this was false. And for doing math over all this, we have to have something formalized. So I kind of consolidated the distinction between formal problems and possibly informal proofs or disproofs. So this is not too unrealistic in the sense that in mathematics we usually know what we're trying to prove, the meaning of what we're trying to prove, or we can more easily formalize it, at least. Lakatos might have disagreed with that, but now, recall that the proof event contains a formal problem and a proof attempt. So what is a problem? Here we will use another idea of Gauguin and Bernstein from around 1990, which is the framework of institutions. Now, an institution is a logical framework. Is a logical framework. They were conceived for abstract model theory, and we will use them here. So what is an institution? We have a signature. For example, for first order logic, we have a category of signatures. For example, a signature is plus 0. Another signature is plus minus 0 and there's a function, of course, there's a function between. So this happens to be the category of signatures for first order logic. We have a functor that for each one of these signatures creates the set of sentences over the set signature. So here we have for each x, whatever. And here we have another set for this signature. And we have another functor for the models, which goes to which creates a category of model for each signature. And between those, we have the satisfaction relation between every model and every sentence. And for something to be an institution, we want this condition to hold that truth is invariant under change of notation. That is, if I take a model of the first signature, let's see here. If I take a model of this signature and a sentence of this signature, then I can check here and check here, and I have the same result. This is quite powerful. And there are institution morphisms. So equational reasoning, equational logic can be considered as a simplification of first order logic. Here we have another signature with its functors, and a morphism between the institution is just a functor here with some, I'm not sure about the direction, with some natural transformations, such that, again, there is a similar condition. So we can translate between logics. Using this, a mathematical problem can be considered as this stuff. You pick an institution that is a logical framework. You can take a signature that is a specific logic. You pick a set of premises, say you want to do group theory, and the claim that you want to prove in that theory. For example, if we're working in first order logic, we might select the signature 0 next plus and then power, have as axioms a first order axiomatization of number theory, and want to prove this little sentence. Now, when we state a problem, we want to see if it actually holds. What does it mean for a problem to hold? It means that from its premises follows semantically its claim. And we usually take it as granted that the premises are consistent. So spoiler number 1, if we have a formal proof of F, we want it to hold. And spoiler number 2, if we find a formal counterexample, then we want it not to hold. And with the definitions I'll present later, these actually are spoilers and not just reasons. Questions over here? Now, given these definitions, we can define relations between problems. That is, if by assuming that P holds, I can get that Q holds, then I say that P supports Q. So that I want to prove Q, but I will not prove Q. I will prove a stronger problem P. This happens to be preordered. The equivalence relation is denoted like this, and we can dually define attack. If by assuming P I can prove that Q does not hold, then Q is attacked by P, and this is a symmetric relation. So these are argumentational notions. An argumentational treatment has already been conducted, but it's quite different. We take some ideas from here. However, now, of course, attacking an attacker does not mean that you support the initial problem, but supporting an attacker attacks the initial. Very important. Nice. Example. I had this little problem, but the truth is, historically, that initially it was stated with these premises that it holds in the natural numbers. And then we axiomatized natural numbers and said that we don't need all these premises, we're fine with these ones. So we weakened our premises and got a stronger inference problem. If we prove that, we have proven that. There are many sub-relations of support that we can define in this framework, and they actually correspond to usual strategies when trying to support mathematical claim. That is, if I stay in a given logic and have a single claim, I can remove some premises, as we did before, and if consistencies are okay, then I can get a problem that supports my initial one. I can try adding premises, and if these premises do not bring something new, then I get actually the same sort of like. I might want to stay in the same logic, but change my to make it semantically equivalent, or change my premises and make them semantically equivalent. Similarly, I can, staying in the same logic, I can attack a problem. I can say, okay, you claim this, but I claim the negation. Or I may attack the premises of somebody else. I can say that, okay, you have these premises, but I keep some of them and arrive at the negation of one of your premises. So your premises are inconsistent. This might happen in more premature mathematics, of course, where we have not concluded that the premises are consistent. And I can change logic. So I can be working some notation, some signature, and want to change the signature. Then, under some condition, if there is a morphism between these signatures, I can translate my problem automatically and arrive at the translation, which I can try to prove. For example, additive duplicative notation or inclusion of a new symbol. I can switch logical frame. Under some conditions again, I can move from equational logic to first order logic. Or the opposite. Under some other conditions. So this can relate statements from different logics. And this is important because mathematics are formalized and stated in quite different logics and logical systems. But if we can find an embedding from one to another, we can use this mechanism to combine this in a kind of unique collection and log exactly the relation between these syntactically very different problems and thus their proofs. We can, of course, generalize support from one problem supporting another to a family of problems supporting another, and have joint support, and of course, dually joint attack. This models the notion of subproblem. So I want to prove that from gamma follows P, but I can break it down to lemmas. Lemma P1, lemma P2, lemma Pn. Or if I have conjunction, I can state it as two problems. First prove the conjunction of the lemmas, and then with all the lemmas prove the result. Now, let's switch to proving objects. Here the situation is more open-ended, and will always be. With all we can define multiple kinds of proving objects. The easiest one to define with this machinery is formal proofs and formal counterexamples. But one could imagine a definition that a plain string is a proof, and we just take it and cannot look inside, but it's compatible with all this. Or intermediate elements can be inserted here. For example, levels of non-formal proofs, partially formalized stuff. LaTeX text that was mentioned yesterday. Or formal proofs with annotations. And somehow we can consider a proof event as a proof. If the community has accepted that my utterance is actually proof, I can take it as granted and use it in another proof event. So in some way we can imagine this like we're above and look down to a whole bunch of papers and say that this paper solves the P1, the other paper solves P2, P2 supports P1, so paper 2 supports paper 1. The other paper attacks the previous paper, and etc. And build the whole graph out of this. We'll talk about it later. And of course, each paper uses stuff from other papers, which has not, usually it's not formally validated. It's just a community consensus that they are correct. This is the intention behind this one. So a formal proof is easy to define because we can have institutions with proofs where we have another functor that builds a proof category where for its signature we have the category of proofs. A proof is a morphism from a set of sentences to another set of sentences. Of course, we can extend the institution to an institution with proofs in many ways. For example, first order, we have Hilbert style, natural induction, or whatever. So here, a formal proof is such a functor that is, and a specific from the premises to the claim. This makes it quite easy to define annotated proofs. We split the functor as a path, and at each path we annotate. At each element of the path we annotate. So that would be an annotated form of proof. Now, we can lift the relation, the property of holding from problems to proving events. It's kind of a mess because when we're disproving, we want the problem not to hold, and this makes reasoning about attacks and supports a little more messy, but we can do it, and thus define our graph, hypergraph, doubt fluent, as a collection of proving events. Every node is a proving event. Every hyperedge is a support or an attack, a joint support or a joint attack, of course. And yes, this can serve as a rational reconstruction of a process of a discussion regarding a mathematical question. Say you start with Fermat saying, I have a proof, I cannot write it here. And this is supported by 3 other papers. Let's say, and this is supported by someone. This has been attacked. So this path is abandoned, and this has been supported, etc. So this framework can, we believe, serve for this kind of modeling of the mathematical discourse. Is quite logic agnostic because institutions are. It descends between syntax and semantics because institutions do. It descends between problem, which is formal, and solution, which might be completely informal. If we have an institution for the prover and an institution for the interpreter, we can discern between presentation and interpretation. As I briefly said, it may be extended to allow for incomplete or annotated proofs. And I have shown that the argumentational notions emerge. Of course, there is a lot to do here. But I don't know if you want to hear. So thank you.
Very much. Questions, comments?
We used these ideas to explicitly mark up, say, the scientific controversy or the development of certain So you might want to actually test your system on the development of Euler's polyhedron formula, which kind of has this back. There's this wonderful book.
Yes, by Lacan.
Yes. And so it might be, and the argument in there might actually be something you want to very concretely get your hands dirty.
In fact, yes, I have not got my hands dirty yet, but yes, the plan is to look at Lacan's next.
So some more questions? Because then we have, after the break, will be the presentation of the teaching software. Hi, school students even. Thank you very much, guys. So I was institute yes, but after I read it, I really like it. So let's take a break because it's so very
No, off the top of my head. I forget if it's really something.
C'est ce qui ressort. Là, c'est Microsoft qui fait ça. Comment? Ah oui, il faut l'acheter aussi. Non, non, ça se utilise comme ça. Ouais.
I was wondering which of the various like case studies that you and me have, like the little experiments that are often found there.
C'est pas
At the least, like this type of the example. Like it seemed nice to me that like quite early is getting into like real non-medical content. Yeah, that's like I can imagine for math AI, like well, this seems interesting abstractly, but like there seems to be real content here, but it's not really like giving an interesting mathematical example. Whereas like that bounded one is clearly. Yeah, it's like an easy feature. But maybe you could export to like PowerPoint and go through that or something. Basically,